In this video, we're going to learn how to find the total number of squares in a rectangle. Notice that this is a rectangle in which the number of rows and the number of columns do not agree. Okay, in one of my previous videos, you've learned how to find the number of squares in a square. However, notice that you can have a rectangle and I want you to find the number of squares. Also, there's another video in which we found the number of rectangles in a rectangle, right? But here's, I want to ask you the number of squares in a rectangle, right? It's going to be a little bit different. And the formula, as you're going to see, is completely different from the formulas that we've derived for the other two videos, okay? So first notice that the technique to find the number of squares when it comes to the graphical way or geometric way is going to be similar to the other video in which we found the number of squares in a square. Notice that first we're going to talk about the cells, which are, we're going to assume that there are squares. And we know that to find the total number of these cells, the smallest squares possible, you just have to multiply the number of columns with the number of rows, right? So that we know the first number of rows is going to be 7. And we multiply it by the number of columns, which in this case is 12. All right, so we know the smallest number of squares, there are 84 of them. Now next, we know that we're going to build this type of shape, okay, in which the number of rows and the number of columns agree, so that makes it a square. Now, how many of this size squares will be there in this rectangle? Well, notice that since we're actually taking up one more square than we did before, smallest square, both to the right side and down, we're going to count fewer for each number. Here, we're going to count one fewer. Our vertex is here this time as opposed to here, right? So we have less room to go until the very end, and the same thing downstairs, right? So we have only 6 positions down, 1, 2, 3, 4, 5, 6, and only 11 positions, including this position across. And notice that you can multiply the number of positions across and down, just like we did in the other video, to save time, right? So note it's going to be 66 of this size squares, okay? Now the next one, as you've probably guessed, is going to be this type of square, right? So we have a bigger square. This time is going to be 3 by 3, speaking of the cells. So again, you're going to have one fewer position to go across and one fewer position to go downstairs, right? So it's going to be 5 multiplied by 10. So that means this size square, 3 by 3, is going to be 50. Now 4 by 4, right? We don't even have to draw anything or count, we just know it's going to be one fewer number each time, right? So it's going to be 4 times 9, and then it's going to be 3 times 8, and then this is going to be 2 times 7, and then finally 1 times 6. And notice we stop there because we've run out of space for the number of rows, right? We only have 7 rows available, which is why the number of columns has to stop along with the number of rows, because we have no more room to go. All right, so it's going to be 6. So now all we just do, we just count these, and we see that it's going to be 280 squares in total. However, if this rectangle is way more huge than what you see here, you're not going to have time to count all of these possibilities, even if you know the highest numbers of the number of rows and the number of columns, right? It's just going to be too many iterations. So best to derive some kind of formula that will save you time in finding the number of squares in any size rectangle. So how do we do this? Notice that we can actually introduce m and n. So m is going to be the number of rows, 7, and n is going to be the number of columns, which is 12. So now if we can determine a pattern using the m and n for any number m and n, for this problem is specifically 7 and 12, right? But it can be indefinitely huge for these two, because we're talking about no limits to the size of the rectangle, right? The parent rectangle that houses all these different shapes. So we just know that we're gonna find the sum as mn. Notice I'm using the product of mn because we started with the product of 7 times 12 plus, and then what? Notice it's one fewer each time for the number of rows and columns. So we have to do m minus 1 times n minus 1. and then m minus 2 times n minus 2, because we're subtracting more and more, right? And then finally, until you get all the way to m minus k times n minus k. Now, what is k going to be? K is going to be m minus 1. Now, m minus 1, because to get to that 1 there, for the number of rows, to get to that last row, basically, you're going to have to subtract the m minus 1. And m minus 1 is exactly 6, right? Because m is equal to 7 based on this very example, right? So m minus 1 is going to be 6. So if you subtract m minus 1, the k value, from the m, you will get the very last row here, right? Because that will be your last row available. You have no more room to go for the m's, right? And notice in this case, it's going to be precisely when m is going to be less than n. What that means is that only when m, the number of rows, is smaller than the number of columns, you're going to use the fact that k is equal to m minus 1. So now, how are we going to determine the sum? How many m times n are there? How many products of mn are there here? Notice there's one product, and using the FOIL method, as you've probably seen before, if you do enough mathematics or algebra, you'll know that these FOIL methods give us the first product of mn. Now, how many of these products do you see besides the first product mn? Notice that there's going to be precisely 6 more, right? Because this is the first one mn, and there's 6 more. So in total, there will be 7 of these products. So that means there will be m products of mn, right? So that means we're just going to multiply mn times m, right? Because there will be m products mn. After that, we have another type of product, negative 1 times m. That means we can just subtract the m and count how many products there are with a negative 1m. Right? There will be one product, second product, and all the way to 6 products. Right? So we have to just do 1 plus 2 plus all the way until we get to m minus 1, right? The kth product. Okay, and k in this case is, as we've determined, is equal to 6, right? Until we'll get to the 6th product. So now everything is in terms of n. Let's continue. Notice the same thing is involving the n here, right? So we're going to have to subtract n here, and there will be precisely m minus 1 products again, right? So we have to do 1 plus 2 plus 3 plus all the way until we get to m minus 1 product. Okay, and lastly, we have perfect squares, right? Notice the last product in the FOIL method is going to be 1 times 1 because the negatives turned into a positive, right? 1 times 1, so it's 1 squared. Then 2 squared because we get positives until we get to k squared. So what that means is that we can just write it as plus 1 squared, 2 squared, 3 squared until we get to the last one, which is m minus 1 squared. So notice that it's going to equal to m squared n. Notice that I'm just combining the m and m together to make it m squared. Then I'm going to have minus m. Notice I can use the summation formula because I know the summation formula of the sum of the first m minus 1 terms can be written as m minus 1. Okay, so we had that m before. Now this involves the summation. So we start with m minus 1 times m minus 1 plus 1, right? Because the term after m minus 1 is just m. m minus 1 plus 1 is just m. All right, and that should be divided by 2. Now finally, what is this going to give us? The same thing, right? So the n multiplies the same sum here that we got, right? m minus 1 times m divided by 2. Right, now, finally, how do we find the sum of the first m minus 1 squares? That involves a different formula, as m minus 1 times m minus 1 plus 1 times twice m minus 1 plus 1, right? So twice, use brackets here, twice m minus 1 plus 1, and this whole thing should be divided by 6. So now, what happens to that? It's getting easier, so it's going to be m squared n, and then we have minus m squared, right? I'm just putting m squared in the front, and then m minus 1 over 2, and then minus mn. So I'm just putting the m in the front of the n in the product, and then m minus 1 over 2. And then plus, I'm going to put m in the front. Notice that this is going to be equal to m, so we can just place it in the front, and then we have m minus 1, and this thing will be 2m minus 2 plus 1, so 2m minus 1. 2m minus 1 divided by 6. All right, so this is getting less and less complicated, so let's see, what does it turn into? This turns into 6m squared n. Now, what am I doing? I'm basically making sure that we get all fractions with the denominator 6, right? So that's what it turns into. And then minus 3m squared times m minus 1. So notice I needed to turn this into a 6. That's why this gets to be multiplied by 3 as well. And then I'm getting minus 3mn. All right, again, multiplying this by 3 because of that needed 6. So that's going to be m minus 1. And finally, plus m times m minus 1 times 2m minus 1 divided by, and this whole thing now divided by 6, right? Because we found the LCD, the 6, for all of these fractions. So now what does it turn into? Again, let's keep simplifying. So we're going to get 6m squared n minus 3m cubed plus 3m squared minus 3m squared n plus 3mn plus 2m cubed. I'm combining, basically distributing all of these so to get rid of these parentheses. All right, minus 3m squared, and then finally plus m, and that should be divided by still 6, right? Because we're keeping the denominator intact. Now, if you combine like terms correctly here, making sure that the powers are matched, and the combination of your variables with powers determine your like terms. Be sure that you follow this correctly when you do your algebra. You should get something like this. You should get m, okay, plus 3mn plus 3m squared n minus m cubed divided by 6. All right, so we have derived the formula that will tell us the number of squares in any size rectangle. Now be sure you understand, this is only going to be true when m is less than n. Okay? When m is less than n, when the number of rows is going to be smaller than the number of columns. You might ask, what happens if the number of rows exceeds the number of columns? Will I need to derive another formula? No, you won't, because there's actually symmetry involved. If you rotate this 90 degrees, you're going to see that all you need is just to switch rows, right? Your number of rows becomes the number of columns, and the number of columns becomes the number of rows. So that means all you need to do is just replace the m's with n's, and vice versa. N will be replaced with m. So now basically what I'm saying, if m exceeds n, we're using a different formula. I'm going to use n, replacing m with n. This product can remain the same, right? Because the multiplication is commutative. Even if you switch rows, it's still going to be 3mn plus. But here you got to be careful. It's going to be 3n squared m, right? Because you're switching places, minus n cubed, all right, divided by 6. Now here's where you got to be careful. So, for example, if you were to use this formula that we've derived, whenever m, let's say, is greater than n, you will get a wrong answer. So basically what I'm saying, when the number of rows exceeds the number of columns, basically if you're trying to test for this shape, and you're using this formula to test this shape, you will get a wrong answer. So basically you can count that there's 3 squares. But if you test the n value being equal to 3, and then n value being equal to 1, because there's one column and 3 rows, you should use this formula instead and not that one, right? This, if you plug in m is equal to 3 and n is equal to 1 into this formula, you will not get the answer 3. So you might assume that I derived the wrong formula. No, you have to use this formula for this shape. In the other video, we discussed once again how to find the total number of squares in a square. So in a square, we would not need either of these formulas because there was a single formula in which the number of columns was equal to the number of rows, right? So that was pretty simple. So the sum, let's calculate it and see if we get the same answer. So that will be what? 7. Now be careful, we're copying this formula, we're plugging into this formula, not that one, right? Because we're talking about when the number of rows is smaller than the number of columns. So 7 plus 3 times 7 plus times 12 plus 3, 7 squared, and this is 12 minus, be sure that you cube this and then divide it by 6. All right, so if you do this right, you should get the same answer as the manual counting method, 280 squares. One last thing I wanted to point out, that whenever m is greater than n and you decide to iterate these by hand, if you don't have that many columns, be sure that your k value, when you try to derive the formula, is going to be precisely n minus 1. All right, so be sure that you don't forget this fact, because k is dictated by the size n this time whenever n is smaller than m. Right? So just like the m dictated when we stopped for the n, because the number of rows was smaller than the number of columns, whenever the number of rows is bigger than the number of columns, the number of columns tells us where we stop. But I suppose you don't really need to worry about that fact, because once you derive this formula, you just switch the variables places and you will be able to figure this one out using this formula without even having to calculate the products and summing them up. Thank you so much for watching this video, and I'll see you in the next one.